Okay, this problem combines a couple different concepts. So we read over the problem. On Easter Sunday, April 3rd, nitric acid was spilled near downtown Denver, Colorado. So this is based on a true reality, something that really did happen. And then the spill was neutralized with sodium carbonate. So we're going to calculate the delta H for this reaction. That's what we need to find. Then we have all of these numbers, approximately 2.0 times 10 to the 4th gallons, so 20,000 gallons of acid were spilled. The acid was 70% nitric acid by mass and had a density of 1.42 grams per cubic centimeter. How much sodium carbonate was required for complete neutralization, so you can see there's a little bit of a stoichiometry component to this, and how much heat was involved. The delta H formation for sodium nitrate is given here. All the rest of those delta H values for formation you're going to find in the chart in the back of your book. So that's where I'm going to pull the numbers from. So if this were a test question, that data table would have to be available to you, or I'd have to give you the values. So authorities were concerned with air pollution during neutralization and considering the high delta H. So that should give you a clue that your value is going to be big when you're done. What was their major concern? So calculation and then kind of an application to this as well. So first thing we're going to do is write the equation for nitric acid. So you'll see there's NO3 here. So nitric acid comes from nitrate, so HNO3. And we're going to add sodium carbonate. Okay, and this looks like a regular double replacement reaction, but if you would do that, you have Na, which is always aqueous, and you have hydrogen as a cation, which is almost always aqueous. So this is an actual decomposition. So the sodium nitrate that they give you is going to be aqueous, but the driving force for this is the decomposition of carbonic acid. So you would get H2CO3, and that's going to break down into H2O and carbon dioxide. So we want the delta H value for this equation. Okay. So all the values that, and let's balance the equation too. So we have 2Na, so that gives us 2 nitrates, so then we need 2 HNO3s. We have 1 carbon with 1 carbon. We have 6 hydrogens here, or excuse me, 6 oxygens here, plus 3 here for a total of 9, 6, 7, 8, 9. So that's balanced as it's written. So I'm going to do negative 207. Okay, since it's taking me so long to write these on the screen, I'm going to pause the video, and again, if you want to take this time to look at your textbook to see where these numbers are coming from, that would be great. So you'll see I've added all these numbers, and these again are all from the table in the back of the book, and they would all have units of kilojoules per mole. I don't have room to write all of that, but again, look at the top of the chart, that's your units. So this is that summation equation of the products minus the reactants. So I'm going to need to take the moles of the coefficients for the moles of each substance times its value. So my delta H equals 2, do brackets, 2 times negative 467 plus negative 285.5, excuse me, 83 plus the negative 393. And you can subtract these if you don't want to do plus and a negative. Okay, just remember to bracket all of that. You want to get that whole concept going there. And then we're going to do another bracket, so we're going to do 2 times the nitric acid, 207.36. Excuse me, negative 207.36. Okay, units really make a difference, so be careful with that. And the negative 1130. 0.8. And we do all of that, we get negative 68 kilojoules per mole. Remember, that's 68,000, so may not be the highest one we've seen, but again, it's exothermic, so that's important that you're kind of thinking that when it says how much heat was evolved, you should get something that is negative. And at this point, it's a stoichiometry problem. So this has gallons, so you'd have to convert gallons to quarts, and then quarts to liters. This information would have to be given to you, so liter's a little bit bigger than a quart. So again, I've just Googled this information. So all of this is just to get your units to milliliters. So I have that density in grams per cubic centimeter. So I'm doing my relationship there. Cubic centimeters to milliliters are the same thing. And putting in my 1.42 grams per cubic centimeter. Now, the other thing I have to deal with is that when I'm going to do molarities here, I only have 70% by mass. So that means 70.0 grams of that solution is HNO3. The rest of it is water for every 100 grams. So I'm just converting that percent. Okay, and let me cancel some units here before we move on to the next liters. I'm not sure what I did there. It's talking about density. But again, it's always good to go back and check, because if that had been an AP problem, you wouldn't get credit for that because it's not the correct relationship. Okay, so that gives me grams of HNO3, so I'm going to do grams to moles, and I'm just going to add up the molar mass of this is 63.02. That's grams in 1 mole. Okay. And I'm just going to put in, so this is kilojoules per mole of Na2CO3. So again, it's asking how much sodium carbonate, so that's how I know what I'm looking for next. So I have 1 mole of, or 2 moles of HNO3 for every 1 mole of sodium carbonate. So I have to convert what I've got. Okay. And then negative 68 kilojoules for every 1 mole of that sodium carbonate. Which gives me a total of negative 4.1 times 10 to the 7th, so 41 million kilojoules. Now if I go back and reread the question, have I done everything? Oh, it asked how much sodium carbonate and how much heat. So this is my heat value. So if I go back through and just kind of do an equal sign here, I can figure out that I have 6.0 times 10 to the mole. Excuse me, 6.0 times 10 to the 5th moles. So it doesn't tell me what unit, so I can leave it as moles. Okay, of the Na2CO3. So that's all the calculation stuff. So this would be sort of like an essay question built into it in the free response. What was their major concern? Well, you got a couple things going on. So you have all this heat. So if I have lots and lots of heat, water is going to be given off as water vapor, which could burn the first responders or anyone else that's still in the area. So that's one issue. Another issue would be I'm getting super large amounts of CO2. So CO2 will displace oxygen, so that could be a suffocation hazard. And again, this isn't all going to happen instantaneously, so if there's HNO3 as this heat's coming off as the first part of this starts to neutralize, you can actually vaporize nitric acid, which also would be very hard on the lungs of anyone who was breathing the air in that area. So lots of things that are problematic with that cleanup there. Okay. So that is a problem with an application of just the summation for the heat of reactions, not necessarily Hess's law, but again, you see how you're applying different skills there.